Music and math, math and music, we might never know which one came first, but we do indeed know they're deeply intertwined. And in the field of number theory, we can find the mathematical underpinnings of musical harmony. To do so, we must utilize a branch of number theory called Diophantine approximation, where we are solving for Diophantine equations. These are equations with more unknowns than equations themselves. Usually we're only presented with one equation, and we want to solve for two unknowns, x and y. The Pell equation is a special quadratic Diophantine equation. We're concerned for solutions for the Pell's equation when d is a non-square integer, because if it weren't, there would be no solutions. There's always the trivial solution when x is plus or minus 1 and y is 0, but we disregard that. There's actually an infinite pair of solutions for x and y, and we solve for them by first finding a fundamental solution, which is the easiest part. And then we find successive solutions by introducing the idea of rewriting the Pell's equation in terms of a conjugate pair of numbers. The successive solutions method is proven in the paper, but it involves multiplying the conjugate x plus y squared to d by itself over and over again. Another thing to point out about rewriting the Pell's equation in this format is that it introduces multiplicative properties alongside the notion of norms, which is very important. The continued fraction expansion way is also described in the paper to find pairs of solutions. The reason why the Pell's equation is particularly relevant is because Stormer beautifully applied the art of solving them into his theorem. The most important theorem, the most relevant theorem, is merely the fact that every Pell equation, in this case, x squared minus dy squared equals 1, does indeed have a non-trivial solution. Stormer came up with a procedure where he found all finite pairs of solutions in a given set of prime numbers. He tested these solutions for degrees of smoothness, and then he arrived at a finite set of ratios in the form of superparticular ratios that in music serve as the backbone of harmony and for every tuning system that exists today. So the given finite pairs of musical ratios are seen here. We first want to think of them in terms of relative acoustic frequency, or inversely the length of a violin string. If we tune the string to an A and play that A, that's the fundamental frequency, and we can describe that as a ratio of 1 to 1. The A vibrates at 440 hertz. If we want to play the A that's higher than our fundamental A, we stub the string in the middle, and as a result, the string is 1/2 the length of the original string. And the higher A, has a frequency that's 2 times that of the lower A. So now we've established this idea that musical ratios can be thought of as frequencies between musical notes, but we want to channel this idea into the notion of pitch rather than frequency. Musical pitch is one and the same, they're the same concept. However, pitch is a more musical term, whereas frequency is a more mathematical term. The idea here is that pitches sound harmonious together when there's a simple ratio between the frequencies of two notes. The ratio of two notes in an octave is a pleasing 2 to 1 ratio. It sounds consonant to our ears. The next most consonant interval is the perfect fifth. And we go down along the lines until we reach dissonant intervals, such as the major seventh, which are no longer superparticular ratios. So the idea is that as the ratio gets more complicated, our brains register the sound as more dissonant and more bad sounding. So the notion is that Stormer used the art of solving Pell equations and applied it to obtain a finitely many number of superparticular ratios. And it just so happens that all of these superparticular ratios, along with their inversions, account for every musical interval that's assigned without hesitation today to the music that we hear in all cultures. The paper will talk about different tuning systems that exist that involve different sets of superparticular ratios, but all of the ratios are derived from Stormer's procedure. And just to wrap it up, an example of stacking constant intervals together would sound something pleasant like in stacking dissonant intervals together, such as the tritone, would sound something like So the next frontier in music is along the lines of 7-limit harmony. So we would apply Stormer's procedure to this set of prime numbers 2, 3, 5, and 7. And we will see that musical ratios from that set of p-smooth numbers is much more complicated than the set of p-smooth numbers 2, 3, and 5.